So our next speaker is Monika Jozsa. She's going to talk about synapse size as a gate between stable and switch-like behavior. Her work applies control theory to neuroscience, and she's a postdoc with Timothy O'Leary at University of Cambridge. I'll pass it over to you, Monika.
Thank you very much, Nidhi. I will share my screen. Can you see it?
Yes, we can.
Okay. Great. So today I'm going to talk about an idea that my supervisor and our group leader, Timothy O'Leary, had some time ago, which is that neurons might use their synapse sizes to elaborate different types of computations. So synaptic potentiation means that after spiking activity, synapses grow. And let's focus on the dendritic spines of postsynaptic neuron. And so when this growth happens, it happens on a much longer time scale than the spike itself. So for this to happen, you need a switch mechanism inside the synapse, which happens through many complicated chemical reactions. And one that's proven to be necessary for it is the autophosphorylation of COMK2. So what happens here, this is a complicated picture, and I won't go through what happens because this is not the focus of my talk. But what happens is that there's a spike coming in, and this enzyme called COMK2 gets activated. And when the spike is already gone, it's still active for some time. So it keeps this signal on. And there is another thing called, it's a phosphatase called PP1, which deactivates slowly this COMK2. So this is how a switch mechanism can happen. But I will get back to it in the end of my talk. So for now, let's take these COMK2s, more precisely the active COMK2s, and free PP1s. So those PP1s that are not busy deactivating COMK2s. And if you take these two populations, then we may notice that they inhibit each other. So we had this more general question, which is, how does a system where there are two mutually inhibiting species present, how does the system behave? And more interestingly, how does it behave when there is a small number of molecules present and when there is a large number of molecules present? So we took this simple mathematical model called toggle switch, where you can think about X as an on mode and Y as an off mode. So these two, let's say, chemical species inhibit each other through these rates, these hyperbolic rates, and they have a linear death rate. And what's important here is this X bar and Y bar, which is going to be, these are just constant parameters, but they will give us the average number of molecules present in the system. And for the time being, we will assume that X bar equals Y bar, and we'll call it the size of the system. So X is like the number of molecules from species 1, and Y is the number of molecules from species 2. So if we simulate this process by setting X bar, Y bar equal 2 and X bar, Y bar equal 100, then we use Gillespie algorithm. And then what we see is that we get this time series. And what's important here is that on the left-hand side, you see this process bumping into the x-axis several times. And this doesn't happen on the right-hand side. So the right-hand side is like a random walk with some attraction line level. And this one on the left is a little bit different. So if we plot the distribution of these processes, then what we can see, as we might expect, is that the one on the right looks a little bit like a Gaussian distribution, but the one on the left is very different. We have some bumps on the axis, and then we have, in this case, a third little bump in the middle. So we will call these modes. And so this system acts a little bit like it acts like a switch. It has these two big bumps, and it spends a big amount of time in each of these. And this other one behaves like a stable system. It is always around its one mode. So that was basically our answer for the first question through this simple example. But in reality, it's really hard to, sometimes it's hard to simulate actual biochemical systems. So it's good to have an analytical tool to at least have a guess what you will get, if it's going to be a bimodal or multimodal system, or it's going to be a more stable like unimodal system. And with this purpose, we applied linear noise approximation for this toggle switch model, which just means that we approximate these processes as like a noise process around this equilibrium, this average number of modes. And if you do that, then you get Gaussian processes, so like a Gaussian fit, around these points. And what's interesting there is that you can see that the probability that goes beyond the axis, so beyond the region of interest, beyond this positive quadrant, is very large in case of multimodality, and it's very small in case of large systems or unimodality. So we wanted to check this for like a more general class of systems. So for this reason, we don't assume that X bar equals Y bar. And also we had a few more extra parameters, K1, 2, 3, 4, instead of just fixing it as the same parameter. And so if we had that, we randomly generated constants. And so every time you have a set of Ks and X bar, Y bars, you get a blue circle here. So what this plot says is that this probability mass outside the axis correlates with multimodality in this class of systems. So going back to the active COMK2 and free PP1 system, when we again have two mutually inhibitory populations, then what we can imagine happening is that at rest, there's not much active COMK2s, but there's a lot of free PP1s. And when there is a spike coming in, then all of a sudden, many COMK2s get activated, and PP1 starts working on deactivating these COMK2s. But there's not enough, in the small system case, there's not enough PP1, so it gets saturated. And due to that, we get another mode. So for some time, the system gets stuck in this on mode, which causes growth of the spine. And then after some time, it goes back to this resting state. But this phenomenon doesn't happen when you have enough free PP1s and a large number of COMK2s. So just to sum up, so we talked about that depending on the system size, we can get switch-like behavior or stable behavior. And we talked about two different systems, but similar in a way. They are both like mutually inhibitory systems of two populations. One is a more biological example, is COMK2 and PP1. The other one is more mathematical model, which is the toggle switch. And we showed we proposed that this switch-like behavior and stable behavior might be used in dendritic spines. So at last, we also talked about an analytical tool to foresee if a system becomes multimodal or not with the linearization of the system and with this overspilled probability mass. So the probability mass that goes beyond the axis. But the bigger question is basically that does biology use this tool, this computational tool, that by changing the size of a system, it can change the core computation, the type of computation that happens within it. And with that, I would like to thank you all for listening.
Thank you, Monika. I think we have a question for you. So the question is from Marcel. He asks, he thanks you for your talk, and he asks, what do you think your findings indicate for heterosynaptic plasticity? Does that mean that a small synapse might be stabilized by big neighboring synapses due to diffusion of PP1 molecules from the big synapse to the smaller one?
That's a very interesting question. So I thought about like supply more through the dendrites, but it's a very which actually can happen with neighboring spines. I didn't actually think about it or use it in the model, but I think it can happen, yes, that neighboring spines stabilize or deactivate this on state.
So Marcel, does that answer your question? Hopefully that answers your question. Actually, since we'll get kicked out of this room in 5 minutes, but since we had